Hi, this is Professor Monty. Let's talk about how to use the second derivative test to find relative max and mins. So the first thing we do is we need to find the critical values. So remember, we take the first derivative, 3x squared minus 6x minus 24, and to find the critical values, we set that equal to 0 and solve. So let's set that equal to 0. We'll solve it. I'll factor out a 3. We get x squared minus 2x minus 8 equals 0. That factors into x minus 4x plus 2. And then we set each of those equal to 0. Of course, 3 can't equal 0, so that doesn't give me an answer. But x minus 4 equals 0 when x equals 4, and x plus 2 equals 0 when x equals negative 2. So those are my two critical values. Okay, so I've got two critical values. So if I've got a relative max or min, they have to happen at those critical values. Well, here's what I do for the second derivative test. I take the second derivative now. So here was the first derivative. I just take the derivative again. And I get 6x minus 6. And what I'm going to do is I'm going to plug the critical values in here. So for instance, if I do f double prime of 4, I'll get 6 times 4 minus 6. Now that's 24 minus 6 or 18, but what I care about isn't the value, but the sign. The sign is positive. And so if the second derivative is positive, remember that what that means, it means the graph is concave up. So if the second derivative is positive, I know it's concave up. Well, if it's concave up, it has to be a minimum. So I know I have a minimum at x equals 4. And then I do the same thing with the other critical value, negative 2. I do f double prime of negative 2, 6 times negative 2 minus 6. Again, negative 12 minus 6, negative 18, but it's negative. And if the second derivative is negative, I know it's concave down. Well, if it's concave down, I can look at the picture. It has to be a relative max. So it's got a relative minimum at x equals 4. It's got a relative max at x equals negative 2. And so I found that if I want the y values, if I need the points, I just plug those x values into the original function. So to find those as values, let's just erase this. And we'll say, well, the y value, f of 4, and I've already done this, so I don't have to calculate it now. It's negative 75. And my y value, f of negative 2, is 33. And so I can say, oh, I've got a relative, let's start here, relative min. Well, the value of the min, or the point where the min occurs, x is 4, y is negative 75. And a relative max, x is negative 2, y is 33. And so now I've finished that. That's how the second derivative test works. If I wanted to graph this, it's really easy to graph now. Because remember, it's a cubic positive, so the graph's going to look something like this. And so it had a relative maximum at negative 2, 33. And it had a relative minimum at 4, negative 75. So the graph looks something like that. And so not too bad. Obviously, the easier these are to factor and find the critical values, the easier this is going to be. But that's the idea of the second derivative test. You put the critical values into the second derivative. If that gives you a negative value, it means it's concave down. Well, if it's concave down, it's a relative maximum. If it gives you a positive second derivative, it's concave up or relative maximum. I don't have to do a chart of signs or anything else like that. So anyway, work with this and it'll come to you. It just takes some practice. So again, if you like my videos, please subscribe. If you haven't already, click like on this video if you liked it, and we'll talk more later.